Hi, my name is NHeath. I'm a scientist at AER, and today I'm going to be discussing using CRIS satellite ammonia observations for improving emissions estimates of ammonia, and then ultimately improving decision making on PM 2.5 control policies. So this is a collaborative effort across many divisions at AER, and then also in collaboration with Environment and Climate Change Canada. So the project is motivated by the fact that there's considerable uncertainty in ammonia emissions. So in the United States, more than 80% comes from agriculture, so things like animal waste and animal husbandry, and then also from fertilizer application. But in large urban centers, we have to account for automobiles, and then we also have to take into account biomass burning and consider different industry processes, and then also the bidirectional flux of ammonia where it can be deposited and re-emitted. So there's a lot of factors going into getting accurate ammonia emissions right. However, this is extremely important because ammonia emissions are very critical to air quality modeling and have a lot of important downstream effects. For example, ammonia is a precursor to fine particulate matter, or PM 2.5, and as we know, this increases the risk of things like respiratory diseases and cardiovascular disease. It can also increase the number of cloud condensation nuclei, which can then have impacts on climate. And then ammonia itself is an important reactive nitrogen species that can lead to soil acidification. And then if it rains and gets washed into a local water body, this can cause algal blooms. And so for all these reasons, it's really critical that we get ammonia emissions accurate in air quality modeling. So one way we could potentially do this is using satellite observations from the Cross-Track Infrared Spectrometer, or CRIS instrument, which can monitor ammonia globally with high spatial coverage. So on the right, this is showing shaded is CRIS observations from April to September of 2013, showing surface ammonia concentrations. And then the dots are showing the same time period for the AMON surface network. And so on the left, these are some of the differences between the two, just to get an idea of the different sampling techniques. So CRIS is a 14-kilometer footprint, whereas AMON is just a point source or a point measurement. The CRIS is once a day, whereas the AMON is 2-week averages, and then also CRIS is looking through the atmosphere, so it's weighted differently at different vertical levels. And so, considering all of those differences, it's encouraging to see that these two different observing networks look pretty similar. So we see that CRIS generally captures the regions where AMON is showing high concentrations. It shows some of these gradients from higher to low. And then we also start to see the usefulness of the satellite and showing us a lot more information. For example, this broad region of higher ammonia concentrations, and then areas where we don't necessarily have observations where we can start to learn more about the ammonia in those regions. To kind of drive this point home further, here's a couple of individual evaluations. One at the top here is at Fort Collins, Colorado, and then on the bottom is at Stockton, Illinois. And so just the take-home point here is that when we compare the CRIS to the AMON, even at these just at these point locations, we're getting correlations anywhere from about 0.7 up to almost about 0.8. And so this pretty decent agreement, despite the significant differences in the sampling, is encouraging and gives us hope that we could take this data and then use it in air quality modeling, which gets us to the overall goal of this project, which is to take the CRIS observations and use them to update emissions estimates and provide more accurate ammonia emissions to air quality forecasters, to air quality managers, and other stakeholders, with the ultimate goal of trying to improve decision making on PM 2.5. So to go about that, this is kind of an overview of our project workflow. So all of this is being done on Amazon Web Services, and it all begins over here with our AQCAS pre-processing. So this is where we're running things like WARF and the ICON and BCON and MSIP, all of the things we need to do to get input data ready for CMAQ. And then as part of our inversion process, we're running 2 versions of CMAQ, a baseline and a perturbed, which I'll discuss in a minute. This goes into an emission scaling factor calculation where the CRIS observations are used to update the emissions and then finally give us an optimized CMAQ that takes into account the differences with CRIS. And then this can be put into an iteration loop, so it's an iterative approach where then this would now actually become the baseline, run a new perturbed, and do the process again. Once we have the final optimized CMAQ, we want to compare with independent data to ensure that it's not just improving things with respect to CRIS, but with respect to other observations. And then in this on the right here is where the users come into play, where we'll have a website set up where users can go in and request emissions estimates for the times they're interested in, the domains they're interested in, and for the model of their choice. For example, maybe it's CMAQ or KMX. So that's kind of the basic overview. The next portion of the talk is really going to be talking, or the rest of it is going to be discussing this inversion process and how we're going about doing that. So here's another little diagram explaining each of the steps along the way of doing this inversion. So it starts with just running a baseline CMAQ, and then what we do is we perturb the input. So we're running this with the bidirectional flux, ammonia bidirectional flux, and so we perturb that input data by 20%. Then we make a separate CMAQ run where we perturb all the other ammonia that's not associated with the bidirectional flux scheme by 20%. And so that gives us 3 runs now. We have the baseline, the bidirectional perturbed, and then the all other perturbed. Using that information, we can then calculate these beta factors, which is explained here. And essentially what beta is showing us is the sensitivity of the simulated surface concentrations to to perturbations in the emissions. So here we're basically relating back this delta in the emissions due to the 20% perturbations I showed to changes in the surface concentration, which are shown here as this omega. And then note that we limit this from 0.1 to 10, and that's just to make sure that things don't go too far in one direction with one iteration, so it doesn't overcorrect in either direction. And then I just want to note here that it's performed separately for each of the perturbations, so we get a beta based on the changes in the bidirectional input, and then a beta based on the all other ammonia input. Once we have those 2 betas, we can then calculate these final weighted emission scaling factors to get us the optimized emissions data set. So I have to show some more equations, but the basic idea is that we start with the a priori, so the baseline emissions from smoke or from the bidirectional input, and then we multiply it by the scaling factor, which is really just looking at the difference between now the observed ammonia concentrations at the surface from CRIS minus the baseline, and then multiplied by that beta factor that we just calculated. And then for each of the different sources of ammonia, so for the bidirectional or the all other, we also multiply it by the ratio of that type to the total. And this is just because we don't want to basically overcount by applying the same scaling factor to both just the BiDi and then to the all other. And so this scales it according to the ratio that it started out as. And then this one again is limited. In this case it's from 0 to 5, and again just as a way to stop things from overcorrecting or going too far in one direction on just one iteration. So once we have those final scaling factors, we then multiply them through all the emissions, and that allows us to run a final optimized CMAQ, which can then be put right back in as the baseline, and the process can be repeated. So now I want to shift over and show you an example of this process at work, and this is using June 2015 as our prototype for testing this. We were using WRF version 3.8. There's some of the WRF settings: the YSU PBL, the NOAA land surface model, the AER RRTMG radiation, and the Grell-Freitas cumulus parameterization, just to name a few. For CMAQ, we use CMAQ version 5.3.2. We were running over the CONUS 12-kilometer domain. We were using the CB6 revision 3 chemical mechanism, the AE7 aerosols, and then at the time here we're running the 2011 emissions. And we're currently updating to the newer platform though. So here are the results for the baseline. So on the left, this is showing for June 2015 the average surface concentration from CRIS, And then on the right is the CMAQ base run average surface concentration. And then on the bottom is the difference, CMAQ minus CRIS. So red colors indicate, or warm colors indicate over prediction, cool colors indicate under prediction. So we can see that near the surface, CMAQ is over predicting in regions of the southeast, under predicting in some of the Midwest areas. And then just kind of scattered over the country, we see mixes of over and under prediction. So as we might expect, when we run the iteration, the final emission scaling factor end up reflecting those changes or those differences. We see, so here cool colors means that the emissions will be reduced, and warm colors mean that the emissions will be increased. And so for both the bidirectional flux input and the all other ammonia, we see similar trends there, just kind of showing that as we would hope, the scaling factors reflect the differences in the concentrations. So when we went through and multiplied the inputs by these scaling factors, and then we reran it, and so okay, this is the baseline again, just to reorient you, and then here is the optimized version. So I'll just go back and forth a couple of times, and so in general, it looks encouraging. If you look at the bottom plot, we see things move in the right direction. We see less intense reds and slightly less intense blues. Looking at the spatial plot, we see much more realistic comparisons now with the two. One, if you just look in the Pacific Northwest, you can see a nice improvement there. And then just, in general, looking better with better agreement with CRIS, which is what we would expect since that's the observations we're basing the inversion off of. So in the final version, we would do this multiple times. We would then, we would take this final optimized CMAQ, rerun it as a baseline like I've mentioned, and go through the process again. But for this beta application, we just did one iteration, and so instead of doing that, we at least want to do evaluate against independent surface data to see if this is in fact improving the ammonia, not just compared to CRIS. So here is the baseline comparison with the AMON surface network, again over that same time period of June 2015. So on the left, the colored dots are just, again, the difference. So warm colors meaning that CMAQ was over predicting compared to AMON, and then cool colors meaning it was under predicting. And so you see some of the same general trends as compared with CRIS, where CMAQ appears to be over predicting in the southeast. We see some under predictions near the Midwest area. And then the correlation among the two is about 0.66. So after we ran the surface inversion, this is what we got. So again, I'll do kind of a back and forth. And so we see the correlation improved to 0.7, and then most of the dots here moved at least in the right direction, although obviously it didn't fix everything, and some did flip. So places of under prediction went to over prediction and vice versa, and that's to be expected from just one iteration. But in general, still very encouraging to see the correlation improve and things move in the right direction when compared to this independent data set. So the next steps for us, as I mentioned, we are updating to the newer version, the latest version of NEI emissions, and that requires us to move to an updated version of smoke. We're also expanding our modeling domain to all of North America, and tentatively we're using a 36-kilometer grid to do that, and then we'll also do a 12-kilometer grid over just the CONUS. We also are developing concurrently, we're developing the software to regrid the emissions to a user's domain and their platform, like I mentioned, whether it be CMAQ or CAMX, and basically setting up that infrastructure so it's easy for other air quality modelers to use this data. And then ultimately we need to automate it so there's less person in the loop, making this really, hopefully as fast as possible for users who are interested. So I'll stop there. I'll summarize quickly and stop. So the goal again is just to take the CRIS ammonia observations and then use that information to help provide improved emissions to air quality forecasters, managers, and stakeholders. In this presentation, I showed you a prototype application of the inversion using bidirectional ammonia flux for June 2015, and it looked to be pretty successful. It improved the comparisons with CRIS and then also with the independent AMON surface observations. And so right now what we're working on is updating the NEI platform, expanding our domain and focusing on automating everything and building out all the code for easy use and make it easy for end users to get the data. So that's all I have. I appreciate your time, and I look forward to any questions you all might have. Thanks a lot.